I've been asked about doing external flow analysis, and I will say, as I've said in the past, I'm not a career analyst, but this should be enough to get your feet wet. So here I have a course there. I've made this in the Curve Shapes workbench. The video of actually making this from scratch is already on the channel, and if you'd like to follow along, you can download this part from my GrabCAD. Let's get started by getting this set up for an analysis. Now, anytime you do an analysis, I don't care if it's finite element, computational fluid dynamics, whatever you're doing, you want to test the simplest version of your model possible. Details equal computation and possible errors. So, as far as this goes, I don't think this propeller is necessary because I'm going to be flowing past the body of the aircraft, and the propeller is just going to get in the way, especially because it will be simulated like it's stationary. So let's get rid of the propeller first and make sure that our model is as simple as we can get it. Let's go to Sketcher. And I care about the ZY plane, so we'll create a new sketch on the YZ plane here. I'm going to draw a rectangle, and we'll import a part of the body here and coincident here. Excellent. Now we'll just take this crazy high, and in an ideal world I would fully constrain this sketch. If you're at this level and you can't fully constrain, then I don't suggest proceeding on. You know what, let's just fully constrain it. 2.5 millimeters looks good, and then vertical 30, right? So let's close that, and then from the part workbench we'll do a revolved cut. And of course you don't really have the cutting on the workbench, but I can say revolve a shape, and of course that will be my very last, and we would want to do it around the Y. So under, there it is, we put a 0 for Z and a 1 for Y, and we're going 360 degrees, so that's looking pretty good. Then we simply select the body of the plane, which in the tree here is called fillet, hold Control, select revolve in that order, and then we choose this make a cut. No more propeller. So now that this is all set for analyzing, let's talk about what kind of mesh that we're going to need to have. If you recall in the previous flow example, we did an internal flow study and we modeled the internal part of a pipe, meshed that, and flowed it. So whatever we model for the meshing, we want to have a solid there. Now that's not always true. In SolidWorks and other platforms you have a different take, where in SolidWorks you need a sealed volume to flow, but in FreeCAD we want to have a solid where we're going to flow. So to accomplish that, I'm going to import a cube. So with our cube, also known as our geometric primitive, I can bump this out a little bit. So we want to do a length of, let's say 100, this is in millimeters, by 200 by, how about 100. And what we're setting ourselves up for is to create this as the envelope of our flow area, and then we cut away the parts that we wish to flow, and then we have, you know, like a negative of it, the same way that you'd make an injection mold tool or something like that. And so we can use this as a negative. So let's go with a position, and let's say Y, move it to -50 millimeters, and then let's do another -50 on the Z. That might have gone to -50 meters. It did. So make it millimeters. There we go. So our plane is right in the middle. Now, a few topics for discussion here. first off is the triad, right? So the triad is not only telling us that our x-axis is along this line, or parallel to this line, because you can see the axes are parallel there, and our z-axis is vertical, and our y-axis is over here, but it also tells us the positive and negative directions. These arrows point into the positive x direction, and going against the arrow will be into the negative x direction. Positive z, negative z, and so on and so forth. So that's how we orient things, by knowing what is positive and negative x, y, and z. Additionally, if we look at the envelope of our flow area, this is for a quick computation, right? Our flow area here is pretty short in front of the plane, and it doesn't go very far behind the plane. We generally want to take the length of the plane, or the length of whatever you wish to flow externally, and make it 10 times that length, and put it right in the middle. And that's a general rule of thumb. And so we're not that far. This is for a real quick computation. It'll be less than ideal as far as the best envelope that we could use. Keep that in mind, right? But I'm not going to spend like 10 hours, figuring this out. I'm just going to do a real quick flow. And with that, let's take our cube, highlight our cut in that order. We'll do a Boolean subtraction. And now we have half the plane in this Boolean subtraction. Now, you might ask, why not do the whole plane? Well, because the plane is symmetric, we can cut the computation in half by doing half of it. Ideally, you can use a symmetric constraint and have it compute both sides of the flow evenly. I actually haven't gotten that to work, but I know it does work. So when we get there, I'll show you what you can do, even though I haven't actually gotten it to work. And then we'll set up our analysis. So we'll go to Part, CFD Open Foam. We'll set up a CFD envelope, and we'll open up this CFD analysis here. Our physics model, we want to make sure that this is viscous with laminar flow. Our fluid property should be air, and that's looking good. We want to initialize fields from potential flow. And then we have our solver. So next, let's build a totally awesome mesh. I'll stand on my cut that I wish to mesh, and I'll click the mesh button. And this should be pretty simple. I'm going to mesh it pretty tight because I've got a small area and I can afford to. Let's go with something like 1.8 millimeters, and I'm going to make sure to specify that unit. And CF Mesh is awesome. If you have trouble with CF Mesh, I've also had good luck with G-Mesh, and I bet Snappy Hex Mesh is good too. But I'm going to stick with CF Mesh, but you can do any of the above. We'll write the mesh case and run. I will also note that this plane is much smaller in scale, so make sure that you mesh appropriately according to your scale, because if this is an actual size plane, 1.8 millimeters is way too tight. So it looks like our meshing is completed. As before, we can load our surface mesh and check it out, and that's looking pretty good. We can clear our mesh as well. Now there's one point that I'd like to make also. You can play around with a mesh refinement, and that's just incredible technology. These developers are just knock your socks off amazing. I'm continually impressed as to what they're able to do in FreeCAD. I'm going to call this an internal volume, and it wants us to select something from a list. I'll choose select from list, and I want to choose my regular cut, right? So the mesh that is around this, we're going to select and say we're going to refine it to 0.75 relative to the other mesh, and I'm going to say done and OK. So now under my mesh, I got this little drop down, and I have my little sub mesh refinement, and of course I'm not showing what I'm actually meshing anymore, but that's okay. I'm going to run my mesher, and I'm just going to show my body again with the space bar so you can get a little bit better of an idea of what's going on. And we're continuing to mesh here. Alright, meshing is completed. Let's load the surface mesh. And again, if you care about really visually looking at your mesh, choose ParaView. Loading surface mesh isn't as visually as accurate. But as you can see, now around the object that I've created, I have a tighter mesh. And the idea behind the mesh refinement is to say, I've got a lot of volume and area that I'm just flowing air through, and I don't need that much definition on. So I can mesh tighter around the objects where I need more resolution, but I can save all the computation and keep it looser around here. So that's how you refine a mesh. And I also want to point out that it might be more standard practice to use a surface mesh instead, and you can specify aspects of your boundary layers. I think 4 boundary layers is pretty standard, with a 1.2 expansion rate is pretty standard, and then you just select from list again. So that's how you do different mesh refinements, right? Your refinement thickness is up to you. I don't know, 4 millimeters or something. So it's something to play around with. I think the mesh refinement for this specific study overcomplicates it a bit, so I won't run the analysis with this. I mean, mesh refinement can give you a lot of definition. It can also be a source of an error. So, be aware that it's a double-edged sword, and it's more computation, of course. But at the end of the day, it saves you a lot of computation if you need a tight mesh. So we've got our mesh here, and I'll just rewrite my mesh case. And while that's writing, I can probably sneak into some of the other topics here. Once we have our mesh, we're going to be ready to solve. Actually no, we'll have to add boundary layers. So I have to determine what is input and output. And I want to use kind of a unique direction on our flow to illustrate ways that you can tackle inlets and outlets and stuff to be a little bit more realistic. All right. Meshing is completed. So we'll close that, and then let's work on boundary layers. I'm going to hide my cut here so you can get a more realistic view of what we're actually cutting. So if I go to my left view, I want not just to flow straight to back, right, front to back, but I want to flow front to back with the air coming upwards a little bit at a slight angle. So let's work on how to do multiple directions, right? First, I'm going to select this face, and I'm going to select this bottom face, and we're going to come here to boundary conditions, and we want to have an inlet. Uniform velocity is fine, and this is where we use that triad trick. We can see the positive y direction, so we're going to specify a positive y value. Let's go with like 50 meters per second, and then a positive z value for a slight upward velocity. And our u of z, let's go with half a meter per second, right? So we're coming up at a slight angle, probably won't be that noticeable, but that is how you can select your faces. Because I didn't just select my front face, I selected my bottom face, and that's for a uniform flow across the cross section. If I were to just specify the front face and have an upward angle of the air and have this bottom face be a wall, then it just won't flow quite right. You won't have like a steady state, right? It'll be flowing up and then it'll try to go against the wall again, and it just introduces more turbulence and chaos. So we're flowing from all the faces that our direction originates from, because we're going up a little bit and mostly from front to back. Let's do the same for these back faces, right? So these other faces are going to be outlets. So I got my faces highlighted, we choose outlet, and that's really all we need, right? No pressure, no velocity, they're just outlets. And so we're flowing from the blue faces to the red faces, and then we want to add a wall, right? And it gets a little bit strange trying to select some of these faces because they're transparent. But I've got that far side wall face selected. And we select this guy. There's our face. We want a slip wall so that we won't create any turbulence as we flow along it. And then what to do here? Well, this is the part where I get a little bit stuck. Usually, to my understanding, you can add a constraint and make it symmetrical. And then whatever flow you have on one side of the face, it will flow on the other side of the face. So if I add that, I say OK because that was already added. Then I've got my symmetry face, but I haven't gotten it to actually be symmetrical. And if you just want to do half, make it a slip wall. And of course, you can just make this cube encompass the entire plane and flow it just at the cost of more computation. That's an option as well. But I think flowing half the plane here is good. Maybe this time I'll get lucky and it will mirror across with the symmetry constraint, but we'll see. Either way, we have all of our boundary conditions we need. Let's go to our solver, and I'm going to write my case, and I'm going to run my case, and then we'll take a look at our residuals. So it looks like we exited with error, and it looks like we have a floating point exception down here. The floating point exception usually means that you divide it by 0, and that often has been mesh size for me. So that doesn't necessarily mean you need to have a smaller or larger mesh, but change the mesh size in one direction. Right, I'm going to say 1.5. We'll write a mesh case, run the mesher, and after it's done meshing, we'll rerun this and see if we don't get a floating point exception. Alright, so our meshing is completed. We'll close. I'll close my failed plot there. We'll go to CFD solver, we'll write and run. And there our simulation finished successfully. My ears are perked up with this upward trend here, but we ended up to be at 10 to the negative fourth, which is generally good results. So for the purposes of this video, I'm going to go with it. Let's open up ParaView and take a look at the results. So ParaView is a very complex visualizing system. And as you can see, we're not looking too bad. This is looking about right. Let's create a stream tracer, and I'm going to show the stream tracer and hide my cube. And of course, lines can be very helpful. I'm going to use a point cloud, and we'll change this to about 1,000 instead of 100 and apply. All right. So it's a little bit hard to read with just a stream tracer, but as you can tell, we have our blue wing here, and we are indeed getting lift on the wing because we have a pressure drop over what about is the 0 point. So we have 0 pressure around here, and we dip into blue as we go over the top of the wing, meaning that we indeed have we indeed do have a drop in pressure, also known as lift. And the reason is, and I think there's still some debates as to exactly the dynamics that cause this, but the air moving faster, to my understanding, over the top of the wing than the air moving slower creates a pressure drop, because anytime you have a moving fluid, there's a drop in pressure, so that's where your lift would come from. And I think the red, white, and blue is the best viewing method, but I can also imply another color method if I try to get a little more color out of it. And that's pretty cool to be able to see that over the wing. I'll move my viewing cube a little bit more over here and apply the new view. There you go. So you can kind of see the body of the plane, right? So we'd hit the propeller up here. We have high pressure, and then we have a pressure drop into the green as we go over the body, and especially the wing. And I can always kind of toggle on and off, right? So you can see exactly what you're seeing over the stream tracer. There are way better ways to view this, I am absolutely sure. My big thing is I'm not that expert on Paraview, so this is about as good as I'm going to get it in this video. But let me actually add some resources into the description that has some step-by-step instructions on how to go even further. So I hope this was helpful. If it was, please subscribe, and I'll see you in the next one.